Okay, so we're going to talk about causality, and I'd like to say a couple of motivating words first, and then I'll say a bit about the structure that we planned for this tutorial. So we will have some exercises that you're going to work on together with your colleagues in little breakout rooms. So this is the link here. Maybe James can also already put it in the chat so that you can try it out. You don't have to install R or Python on your computer, so this should ideally run online, but it's fine because you're going to work on this in groups of 2 or 3 people. It's fine if it just works for one of you. So then you just, so what I will propose later when you work on these exercises, you will be together in a small breakout room, and then let's say the person who comes first in the alphabet, if you look at the first name, this person just shares the screen, and then you can work on these exercises together. There's a little trick. So if the notebook is inactive, rather than, because at the beginning it might take a minute or so to load this, because it loads a couple of packages. So you can always use kernel and then restart. This will be actually faster than just reloading the web page. This is a little tricky. And the code will be available in R or Python, so you can choose. Okay, so there's also a disclaimer. So this tutorial clearly presents work by many people, and we are maybe sometimes just out of time and space, a bit sloppy on the references. A more complete list, if you like, can be found in this book. So you can just go through the MIT website, and then you will find an open access version of this. So you can just download the PDF for free. I think I put also one on my website, actually. And of course, so we are always more than happy about feedback about this book that we wrote a couple of years back. In particular, we are going to talk about one language. There are different languages that you can use in causal modeling. We are going to talk about structural causal models. You can also, for example, talk about potential outcomes. I'm happy to discuss a bit the differences, but you should really look at this as 2 different points of views of formulating causal questions, and both have their advantages and disadvantages. We are just focusing on one today. This is the structural causal model side, but here are some references where you can also read on the other side. Okay, so here, this is one of my favorite examples. It's a thought experiment. And now what I'm going to do is I'm going to try to convince you that for certain types of questions, we need to talk about causality. So let's see whether I succeed with this. So look at this scatter plot here on the left. So on the x-axis, we look at the oops, I should mark this here, of course. So we look at the activity of a certain gene, and then on the y-axis we look at a certain phenotype. And clearly you see that there's a correlation. There's a correlation in the data. So clearly there's a dependence. Now, what we are now very good at, and I mean, you hear about all these success stories, of course, also in the newspapers, is at prediction tasks. So given a certain value, let's say in this case of the activity of gene A, what is the best prediction for the phenotype? So now, for example, if let's say we observe that the activity of a gene A lies around 4, so then what is the best prediction of the phenotype? Well, maybe then it lies around this value, so around 10-ish. A different question, however, is what is the best prediction of the phenotype if we intervene in the system and let's say we delete the gene A. So we actively set this value to 0. So this you can do. So I mean, we cannot do it, but biologists can do this in simple systems like these. You can delete a gene, then the activity is 0. And then the question is, well, what is the best prediction of the phenotype? And the answer to this question must depend on some causal structure. So why is this? So imagine that we have a scenario where the gene A is really causing the phenotype, and we will be more specific about this later. So then if you now delete the gene A, you also expect a decrease in the phenotype. So the best prediction interval is around here. On the other hand, if let's say you have a similar scenario where you have a gene B that is also shows actually the same dependent structure with the phenotype, but has a different causal structure. So now in this scenario, we have a so-called confounder that is influencing both gene B and the phenotype, then the answer to the question is different. Because now if you delete gene B, so you put a hammer and you destroy somehow the gene B, the question is what happens to the phenotype? And the answer is, well, not much, because the phenotype really doesn't care about what you did with gene B. So therefore, the best sort of prediction for the phenotype is to say that it does what it usually does, so it lies in this area here. So what does this mean? This means that if you want to answer this question of what is the best prediction of the phenotype under an intervention, you have to talk about causality. And now is the last opportunity for you to sort of complain. Because if you don't complain now, you have to listen to causality for the next 2 hours today, and also, I think, almost 2 hours tomorrow. Okay, so no complaints so far. So now, of course, in reality, and we are not talking much about this, in reality, the questions are more complex from a couple of different angles, and one of them is that in reality we may have more complex data structure. So the slide I showed before, this looks a bit like an IID data set. But if, like here, this is an example where some colleagues from us approached us and asked us whether we could collaborate on a certain question where the question was about the causal relationship between violent conflicts. Here you see this in the country of Colombia in South America, and deforestation. So the red dots here are violent conflicts, and the blue shading this indicates forest loss. And now if you look at a question like this, then this is a very strong spatiotemporal structure, and you somehow have to deal with this. This is something we're not going to touch about today, but just to let you know, I mean, the questions are very similar, because also here it could be that there's a confounder that is influencing both. So we see that there's a strong dependence, right? So the conflicts seem to be in the areas where there's also deforestation. But now if you're asking about causal influence, then we also have to somehow make sure that we can deal with confounders. So here, this is just to show you one confounder. This is the same conflict data, but now the blue shading is different. Namely, this is now population density. And you can imagine that both deforestation and violent conflicts sort of tend to happen in the areas where you have people living. So this means that if you're trying to estimate the causal effect from conflicts on deforestation, then you have to somehow deal with these confounders. So this is a very similar sort of similar structure as we saw before, but now with a more complex data structure. Okay, so now this is the one and only most important slide of this talk. So what is a causal model, right? So how can we formulate all these questions that I talked about earlier? How can we even make them mathematical? And this we can do with the help of causal models. And as I mentioned earlier, there are sort of different causal models we can, or different formulas we can use. And we are going to talk about one that is called SCM, or a structural causal model, that I'm going to introduce later. Now, very importantly, I think this picture, at least it helps me to understand what is a causal model. So we are very much used to modeling observational distributions of data. So think about just modeling a data generating process with a multivariate Gaussian. Now, a causal model should be able to do that, but it should also be able to do something more. Namely, it should be able to model all these interventional distributions. So it should be able to predict what happens if I delete a certain gene A. A classical statistical model that we learn about in Statistics 101 is not able to do that. But a causal model should. So in some sense, you can think about this as being a bit more of a powerful modeling technique. Now, it also outputs, and this is our view on things, so it also outputs a causal graph. So we are saying that this is some sort of a visualization of the underlying causal model. Some people would put the graph in a bit more of a central, give it a bit more of a central meaning. But for us, so you can talk about causal graphical models, but for us, it's really just induced by the structural causal model. And then there's also something that are called counterfactuals that come out of these causal models. And this is something that we don't talk about today. Good. Okay, so what are we going to talk about in this tutorial? And I'll keep an eye on the questions and see when they make sense. So the first part that we need to talk about, and this takes about 15 or 20 minutes, this is the part where we are looking at, we have to define what is a causal model. And I think that's actually quite rewarding in the sense that it's a very simple tool. It's, I think, relatively simple in terms of mathematical technicality, but it's quite powerful in the sense that it allows us to formulate a lot of these interventional questions and causal questions in a very precise way. So this will be the first part where we look at the we define the causal models, and we will see in particular how do they induce a distribution P, how do they induce a graph, and how do they induce interventional distributions. That's the first part. And now, what are the questions in causal inference that are asked? So if you look at this as a research field, then there are a couple of questions that are studied. One of the questions is as follows. In reality, you are never given a full causal structure, but maybe you are only given the causal graph, maybe from background knowledge. Maybe you talk to an expert in the field, and the distribution P. And then the question is, well, can we somehow use these two things of information to infer something about interventional distributions or causal strength, for example? So this is one of the questions that is studied. And we are going to talk a bit about this in the second part. Now, another question is, well, maybe you don't even know the causal graph. So maybe there is no domain expert that tells you what the ground truth is. And then the question is, well, can we somehow infer, if we only have data from the distribution, can we then somehow infer something about the causal structure? And maybe we don't only have observational data, but we also have a bit of interventional data. So then going from the distribution P and the interventional distribution to the causal graph, this is another question that is studied. This is often called causal structure learning or causal discovery. So we will also touch a bit on that. Now, thanks a lot for all these questions. Maybe I'll look through them after we talk a bit about this causal model, because this is really at the basis of everything. Okay, this is one more way, and this hopefully it helps. If it doesn't help you, then you can just forget about it. This is like a point of view that helps me think about these things. So if you think about models, then you may think about a hierarchy of 3 different models. I mentioned this already. On the bottom, you have a statistical model that is, think about the multivariate Gaussian. And the top, this is sort of the best thing to have. This is a mechanistic or physical model. And here you can think about like a set of differential equations that is, for example, constructed by first order principles. So let's say you think really about physics, and then these models, they also tell you, well, what happens if, for example, you set a certain temperature or you increase the pressure, for example. So in a way, these are the best models to have. And what we are now studying is something that you can think about being in between, because these causal models are still able to say what happens under an intervention, but they don't give sort of as much physical understanding. And now you can be wondering, well, is this ever useful? And I would say yes. For example, in the medical domain, we have, in a lot of situations, we are dealing with these causal models. So for example, if you undergo surgery, then you take this anesthesia, and in many situations, it's not clear at all like how exactly the anesthesia works, what happens in your brain, but we have a good understanding of how to use it. So how much to give, like not we as in the doctors, so of course I have no clue about this, but the medical doctors know very well how much to give to a certain patient who weighs a certain amount of kilogram, for example. So here we have a very good causal understanding, even though we don't have the physical understanding of knowing what happens in the brain. And I would argue that this is in a lot of scenarios, this is very useful to have. Maybe the only column that I mention here is this one, the falsification. So if you think about Popper, for example, saying that you should be able to falsify models, then this is something quite important to keep in mind, because a statistical model you can only falsify by looking at observational data. And then, for example, you see, well, the data really don't look like they're Gaussian. So then you can falsify the model. However, if I'm selling a causal model to you, then you can falsify this also by looking at interventional data, because maybe then you can just perform an interventional experiment, increase the temperature, and you see, no, in reality, something very different happens from what you claimed or your model claimed would happen, and then you have falsified my causal model. Okay, so this is maybe another way of looking at this. And now we come to the vegetable, or whatever you want to call this, so to the content. So what is a structural causal model? Here, this will be only a couple of slides, but you will be hopefully amazed by how simple it is. Let us assume that we want to model the causal relationship between two random variables, x and y, where x is the altitude of the place and y is the temperature. So now, what is a structural causal model? Structural causal model just contains of two assignments, one for x and one for y. And here I chose a very simple form. So x is just a noise variable nx, and y is just -6 times x plus some noise variable. And the noise variables here are IID Gaussian 0, 1. Where does the -6 come from? Well, this is this idea that if you climb 1,000 meters, then the temperature drops roughly by 6 degrees. Now, the first question is, well, why does this induce an observational distribution over x and y? So here, if you look at the system for a bit, maybe you see what kind of distribution it induces. So the nx and y are Gaussian and independent. Everything is linear here. So the overall distribution over x and y, this will be a vector, and this will have a Gaussian distribution. So now the question is, what is the mean, right? It should have a mean, and it should have a covariance matrix. Now, what is the mean? So here everything has mean 0, so also the mean will be 0. And now the question is, what is the covariance matrix? So, for example, you can think about what is the variance. So one of the components here is the variance of y. So what is the variance of y here? So if you look at this, just for 15 seconds, maybe you can find this out. So this will be 37, right? Why is this? Because we have the -6, this goes out squared. So then we get 36 times the variance of x, this is 1. And then plus the variance of ny, this is also 1, so we get 37. So you can also think about the covariance matrix, and then if you just do the computation, then you see that the covariance of x and y is -6. So what do we get? We get a distribution over x and y that is Gaussian with a certain mean and a certain covariance matrix here. And now, maybe what also helps to think about is to think about these two lines as lines in a computer code. So if you want to simulate from this distribution, if you want to generate one observation, then you would first generate an observation for nx, then for ny, and then for x, you just use this equation here, and then you can generate the one for y using this equation. Okay, so this induces an observation distribution, but we said it should also induce an interventional distribution. And how does this work? Well, this is very simple. The only thing that we do is we replace one of these assignments. So here we just replace it by x being 3, for example. So this corresponds to an intervention, and this means that we take a place like Copenhagen, and just elevate it by 3,000 meters. So we put this place at 3,000 meters, and then we see what happens to the system. And this is, of course, intervention that is very hard to do in reality, but in mathematics, this we can just model very easily by just replacing one of these assignments, namely the one for x, and we just set it to 3. And now this again induces a distribution over x and y, but this is now a different one. It's actually like all the marginals, the distribution for x is different, the distribution for y is different, the covariance is different. So more or less, like a lot of the things are different. If you write it down, the precise form of this new distribution doesn't really matter. So it's a degenerate distribution, right? Because it always takes the value 3. Now y is still Gaussian, but suddenly has a different mean. So you can do the math and you can get this distribution. The precise form doesn't matter, but what is important is that we give it a different name. And why is this? Because this is now a distribution under an intervention. And what do we call this? Well, we give this famous do notation. So we call this the distribution under the intervention. Opala. So now my tablet decided to intervene in my presentation here. I don't know why. So what happens here is we are intervening and we are sort of setting one of the variables to 3, and this we want to like also indicate in the notation for the distribution. Okay, let me just check whether I can find my tablet again. Otherwise, this doesn't matter too much because I can just stop the sharing here and share the talk on my computer. That should work as well. So apologies for this. I don't know why my tablet decided to do that. Okay, so now hopefully you see the slides again. And this is the one here that is now induced. So P do X being 3. And of course, similarly, no surprise, you can also intervene on Y. So this would correspond to an intervention where we are saying, well, you just build a glass dome around a certain area and set the temperature to, let's say, like a Gaussian with a mean 2 and a variance 2. Again, this is an hypothetical experiment, but importantly, we can model this very easily in mathematics by just replacing one of these lines in your computer code, if you like, by replacing one of these assignments. Again, this induces a distribution that we again call an interventional distribution, and we just give it a different name now because we have to indicate that this is intervening on the variable y. Okay, and now, so just to clarify, right, there's nothing special about two variables. You can do this with as many variables as you like. And here you see an example of a structural causal model over 4 random variables. So again, you have this these lines of computer code, if you like. And here I chose a linear form, so everything is linear. Here we have 4 noise variables, and we have these assignments here on the left. Now, I should maybe say, what is this graph? So how do we induce the graph, right? This was the other property that we need from a causal model. So this is quite natural, I hope. So you just always draw an edge from the variables that appear on the right-hand side to the variables that appear on the left-hand side. So here, for example, there will be an edge from x3 to x1, because x3 appears on the right-hand side. Now, if you have a training in mathematics, you of course now want to maybe make this a bit more formal. This can all be done. We've just published a very long paper about this, including the measure theoretic details. But fortunately, we don't have to worry about this today. What we are going to assume at least today, for today and tomorrow, is that these graphs are acyclic, so they don't have directed cycles. Is this important? So you can relax this, but it makes it easier. So in particular, maybe if you like, in a break, you can think about this. This makes it much easier to say that there's a distribution induced by the structural causal model. So for today and for tomorrow, the graphs will not have any cycles, but of course, I'm happy to discuss the possible extensions there. Okay, and now again, this induces an observational distribution over x1 to x4. I'm not asking you to write down the covariance matrix. It looks like this. If I didn't do a mistake, it looks like this. So again, the precise form doesn't matter. What is important, this is the observational distribution induced by this, structural causal model here. And again, you can intervene. So for example, if you intervene on x1, you're just replacing the assignment for x1 and you just set it to 0. Again, this is a mathematical model for an intervention. And here, what you now also see is that, I mean, the functions here, they don't have to be linear. They can be anything. So here, for example, this is we just write it in the form of saying a function of x1 and 2, and here the x1, because x1 enters the equation for x2, right? So then x1 is sometimes called the parent of x2. And if you think about this for some time, it's a bit hard to see when you see these models for the first time. But if you play a bit around with them, that you realize this model structure is extremely general. So this allows you basically to model any conditional distribution of x2 given x1 that you may think about. So these models here are quite powerful. And even if you look at the whole bit, so if you allow for complicated functions here, then you can model any joint distribution over x1, x2, x3, x4 can be modeled by this by such a structural causal model here. Okay, so maybe two more things to say. So one is, and this I want to mention already now. So one thing that will be quite crucial for a couple of arguments that we do later today and tomorrow is that if you look at an intervention like this, so you intervene on x1, then as I said, right, so it uses a new distribution that we call P do x1 being 0 because you intervened on 0. And now what is important is the following. So this distribution will now differ in many aspects from the observational distribution. Many things will be different, but they are not arbitrarily different. And why is this? Because a lot of the components here in the system remained the same. So for example, if you intervene on x1, you don't change the structural assignment for x2. So this will still be the same no matter what you did before. The same for x4. You're not replacing the assignment for x4 if you intervene on x1. And this is actually an important part. So this is sometimes called modularity or autonomy. And to the best of my knowledge, that all the concepts of causality that I have read about and I have learned about that are somehow possible to operationalize so that you can do mathematics with them. All of them have this type of modularity in some form or the other. Namely, this idea that if you intervene on some parts of the system, other parts of the system will remain the same. This is quite a crucial concept that is sometimes a bit hidden in sort of these definitions of structural causal models. But this is what I wanted to already mention because we will come back to this later. Okay, and now I suggest that James takes over and we do a little exercise on this so that you can see how these things work in practice. It's a small, little, hopefully not too difficult exercise, but that gives you some idea of what's going on. And then afterwards, I suggest, so James will introduce you into this topic, and afterwards we will discuss some of the questions that you have posted in the chat. Okay, yeah. Then I stop sharing now, and James takes over.
Thank you. Actually, I think there's one question in the chat that about.
Thanks a lot. So this, of course, we should do before. Yes, is there a difference between intervention and dependence among random variables? That is a very good question. So thanks for that, James. Let me just go to this one first, and then we do the exercise. The answer is yes. There is a difference, and it's a big one. So maybe I give 2 examples for this. So let's look at this example here with the altitude and the temperature. Now, let's say we are looking at a certain country, right? So we are looking at different places in this country, and then we have a distribution of altitude. So in Denmark, it's pretty low. In Germany, it's a bit more mixed because there are the Alps in the south. So let's look at Germany, for example. Then we have a certain distribution of altitudes over this country. So if you take a randomly chosen city in the country, it has a certain distribution of altitude between 0 in the north and I don't know, the Zugspitze, I think, is the highest mountain in Germany. Now, if you condition on the average yearly temperature, so if you're taking a random place and we condition on the fact that we know the average temperature is pretty low. So let's say, I'm now making something up, let's say it's 4 degrees. Then we know that this place must be high up in the mountains. So then suddenly the distribution of x given or conditioned on the fact that we sort of observe that the temperature is low, then the altitude is relatively high because we know that it's colder in the mountains. However, if you intervene, so if you look at the distribution of x and you intervene on the temperature, so this means like we are taking a random place and we are setting the temperature, we are building a glass dome around it and we are setting the temperature to a certain amount, then the distribution of x didn't change. So then it's still, because we don't know, then somehow this temperature doesn't tell us anything about the altitude because we set the temperature actively. So this is hopefully an intuition why the do intervention and the conditioning is very different. And just a second example, because it's such an important question. So in this example, it's similar. So if x3, for example, x3 has, let's say on x1, so if you look at the first assignment here, right, x3 has a positive influence on x1. So now imagine that you condition on the fact that x1 is very large. So then this tells us something about x3, right? Because, well, if x1 is very large, then it could be that just the noise was large or that x3 was large. So if you condition on the fact that x1 is large, then the distribution of x3 changes, because then it's a bit like a Bayesian way of thinking, right? Then it's actually likely that also x3 was large. However, if you intervene on x1, so if you intervene and you just set x1 to 1000, then this doesn't change anything about the distribution of x3. So in the conditional distribution that x1 is 1000, then the distribution of x3 changes. Whereas if you intervene and you look at the distribution do x1 1000, then x3 is still a Gaussian 0-1 distribution. So hopefully this clarified things, and if not, then ask again after the exercise, because we are going to look at this now in the exercise. It has nothing to do with noise. It's the same argument if you use noise. So. Okay, James, I think you can take over, and I will reconnect to this Zoom and hope that the lagging becomes better.
Okay, sure. Yeah, so let me first, I hope everyone can hear me okay. If not, let me know. So let me first post the link in the chat again. So I think you can all go to this GitHub page, GitHub link. And let me also try to share my screen. All right. I think you can all see my screen now. Yeah, so you have 2 options. You can either use Python or R, but I'm gonna be using Python for the solution. And also you can choose to open the exercise with, for example, Google Colab, if you prefer it, or we also have this by the option. And for me, I will just use Colab because this is what I usually use. All right, so if I just open it. Yeah, so here we actually have 5 exercises, but today we're going to go through only 3 of them. But for this session, we will focus on the first one, the structural causal model. So you basically have to basically do this exercise 1, structural causal model. And this is quite a simple one, but I think it's also a very important one to show you how the SCM actually works in the code. Like Jonas said, it's very simple. If we just put in the code, actually, the mechanism underlying SCM is pretty simple. So here we have a bunch of variables, and this is the SCM that we have here. And the first thing we just ask, what are the parents and the children of X in the SCM here? So this is the graph. So the SCM also induce a graph. And we just ask what are the parent and the children of X in the graph that induced by the SCM. And then you take a pair of random variables here and think about whether you expect this pair to be dependent or not. And from this sample that we have, all right? And then you just check this empirically. And by empirically, you can, for example, plot the correlation. And next, we ask you to generate sample from interventional distribution. So now what you need to do is you just take this SCM and do the intervention on X by, for example, replacing this X, this line of code with the Gaussian, this Gaussian distribution here, and then you sample from that SCM, and then you just answer this question, and then you can also check the empirically by doing some plots. All right, and I hope this makes sense. Otherwise, you can always ask the question here. So next we're gonna just, let's see. Yeah, next we will put everyone into breakout room. I think it's gonna be the same breakout room. And also I encourage people to open I think Jonas, you were saying, did you say something? Because I couldn't hear you, maybe. Okay. So yeah, so we put everyone into breakout room, and I encourage people to open the camera. For this one, let me share my screen again. Okay. And again, if you have any question, you can post in the chat directly, and I will try to answer them. All right. So I think the idea of this exercise to just show you how easy the interventions are, or like how does it look like in the code. So let's go through the exercise. So here we have this SCM here, and the first one we asked about the parents and the child of X. And what we can do, we can actually draw the graph that induced by this SCM. And like Jonas mentioned, we can draw it by look at the structural equation, and in the code, it's just basically a line of code. So here you can see that if the variable appear on the right-hand side of the code, then you just draw this variable, this node to the arrow from A to K, for example, here, and you end up with this graph. So the parent of X would be A and C in this case, and the child of X would be F. And now next question, if you take a pair of variables and think whether you expect this pair to be dependent or not. So here, if I take K and G, for example, here, K and G, yeah, it's not super obvious how K and G from the graph, but you can see that you can there should be some dependent between K and G, because A also affect K and A also affect G in this path, right? So if you plot it, then there's a strong correlation between K and G. All right, and now the next question, maybe this is the main question. So we ask you to sample from interventional distribution, and what we can do here, we just copy the code here, and then what you do next is just replace this X, the line of this single line of code here, by the distribution that we want to replace. So here we want to replace X by a Gaussian with mean 2 and noise 1. So what I can do is just put R norm n here and then plus 2 to be a mean 2. And again, you replace one single line and you don't change any other lines. So this is the modularity property of the SEM. So you really change only one equation here, only one line of code. So it's super simple to get the interventional distribution. And now you can get the distribution. And next, okay, the question is, do we expect the marginal of Y to be different from both samples? And we can actually, if you look at the graph, maybe this is the easiest way to think about it, by looking at the graph. So you can see the X here really influence D, and D influence Y, right? So we can kind of expect that if we change something with on the X, then it should really change the distribution of Y because of this this path here. And the answer is yes. And we can actually check imprint. Okay. Okay, let's do this one first. So now the next question is, do you expect now the joy distribution of A and Y to be different from both samples? And this may be a bit maybe trickier to answer, but it's actually also quite simple. So here we intervene on X, right? And we ask if we intervene on X, whether the distribution of A and Y, the joy distribution of A and Y will be different or not. So the idea is that when you so in the observational regime where you don't intervene on X, A and Y are like dependence in two ways. Like you get dependence from A to K to Y, and also A to X to D to Y, right here. But when you intervene on X, you essentially cut the arrow from the parent of X. So there is no real, like X and Y are now, sorry, A and X, you cut this arrow out. So now you can kind of expect that the joy distribution of A and Y should then also be different, because there's now no connection from A to X to D to Y anymore in the interventional distribution. And we can then look at the plot to check if it's true. So first here, this is the marginal distribution of Y in both regimes. And we can see that it's quite different. I mean, the mean is obviously different. And next here, this is the like a correlate, like scatter plot between Y and A in both regimes. And we can see that obviously the joy distributions are different because the correlation just really flipped the sign. Okay, I think that's all I have to say for this exercise. And if you have any question, you can also put in the chat. Otherwise, I just give it back to Jonas.
Okay, great. I hope that you can hear me okay. I suggest we just do a very short break, maybe 2 or 3 minutes. Everyone can just stand up quickly, get some fresh air or a coffee or some glass of water, and then we meet back at, so okay, for us it's 28 minutes past 10, but this is of course very different from all of you. So just in 3 minutes so that everyone can get some fresh air before we continue. Okay, so welcome back. There are lots of good questions in the chat. I would like to comment on some of them now and on some of them later tomorrow. So, but I have received them. Many thanks for the to the volunteers here. So that's great, and hopefully I will not forget. So one question here is now is in relation to Bayesian networks. I think it's a good one because these. So what we will. Okay, maybe I should say one thing first. So there is something that is called D-separation, that is a graphical criterion for deciding a purely graphical criterion. It has nothing to do with probability distributions. That is a notion of whether two nodes are separated in a graph given another set of nodes. This is called D-separation. It's something that we didn't plan to talk about. If you are interested, we can do this tomorrow. We didn't plan to talk about, but it's a useful concept. So I encourage you to look at this. There are many other separations, but I think they are less important. So the D-separation is something you can have a look at. It's also, we explain it also in the book if you want. Now, what is a Bayesian network? A Bayesian network is now, if you like, it's a tool for modeling distributions where you say that a distribution is Markov with respect to a graph. What does this mean? This means that like a graph has certain of these D-separation statements where you can separate nodes and so on. And the Markov condition now says that, well, whenever you have a D-separation in the graph, I assume that this implies a conditional independence in the distribution. Now, a Bayesian network is basically saying this. So it's saying, well, I assume that the distribution that I'm trying to model is Markov with respect to this graph, meaning that whenever something is separated in the graph, then there is a corresponding conditional independence. Now, importantly, Bayesian networks, so I mean, it depends on the user, but most of them would say they do not model causality. In particular, this means that you have many causal models that are, many Bayesian networks that for a person working with Bayesian networks are entirely equivalent. So I can put two of them into the chat. So this one and this one, these are two Bayesian networks. And for a person working with Bayesian networks, they are entirely equivalent. They don't, I mean, there's no reason in distinguishing between them. Why not? Because they induce exactly the same dependent structure in the data. So namely, they say here that X and Z must be independent given Y. However, from a causal point of view, they are quite different. Because we are also assuming these interventions, right? We are also trying to model interventions. And this is something that usually a person using Bayesian networks does not want to do. So this is one of the, why, I mean, I know that someone retracted the question, but why I thought it's nevertheless an interesting point. One more point regarding the noise. There was a question in the chat. I think that's also an interesting point. What if we remove noise? So then the concepts all go through. That is fine. They are becoming a bit more tricky because one has to think about what does it mean that something is conditionally independent and so on, but it works through. What I wanted to say, however, is that the notion that we have of a structural causal model here, this is a model, right? So I can write down any model that I have or that I want. And now the question is it correct or not? But here I wanted to add that these noises somehow enter into the dynamic in the sense that they are really, so the N2, for example, X2 has a noise component, and this noise component also then enters into X4. And this is just something to be aware of, because another, I think also very realistic scenario is where you have some dynamical systems, let's say some causal structure and something happens, and then you have observational noise on top of this. So this here is not observational noise that you have on top. So this is really noise that goes into the causal structure, if you like, into the causal mechanism. Okay, is this statement true? Is another question. In Bayesian network, information flows in both directions, but in causal network, it flows only in the direction of error due to intervention. Well, I think that's not. Let me put it this way. I think that's not incorrect. The question is, however, what does it mean that information flows, right? So what does it mean that information flows? If you want to make this precise, then maybe you end up with a causal notion again. So I would rather think about Bayesian networks as saying this only induces conditional independence constraints on the distribution, whereas a causal model induces a lot of constraints also on interventions. Okay, so a couple of the other questions I will address tomorrow, except for this one question that related to this intervention, that whether they have to be radically different. For example, because I mentioned the value 1000, they don't. So this difference between or the point that doing and conditioning is in general not the same, this is also true for smaller values. Just wanted to make the point. I thought it's easily seeable with the large values. Okay, so now here's again the graph that you saw, and now I want to highlight one specific fact. So we are still in a setting that's very important. We are still in a setting where we know the causal structure. Some expert has given it to us. Tomorrow we will talk about what happens if we don't know the causal structure, but for today we know it. And now, if you look at this graph, then in some scenarios you might be interested in what is the causal effect from X to Y. So how strong is the causal effect from X to Y? And this, I would say, happens in many real life scenarios. So if you are interested in, of course, vaccination effects or something, you are interested in a causal effect. If you're interested in nutrition, so for example, there are many observational studies, right, where you see that certain people who eat a certain type of diet seem to be on average healthier than other people. So here X could be the diet and Y could be the health status. But now this could be confounded because maybe people doing a lot of sports tend to choose this diet, and maybe they are more healthy, not so much because of the diet, but because of they did more sports. So here A could be something like doing sports. Now, in such a scenario where you're really interested in the causal effect, then the point is as follows. If you just look at the dependence between X and Y, and this James also mentioned during one of the explanations, if you're just looking at the dependence between X and Y, then there are two paths, so to say, that contribute to the dependence. One is the directed path from X to D to Y. This is what we are interested in. But somehow this confounding path that I plotted in red here, this also contributes to the dependence between X and Y, and in a way that we don't like. Why? Because this is like not what we are interested in if you're interested in the causal effect from X to Y. This is the confounding path. This is the influence that maybe sports has on choosing the diet and then being healthy. So now one type of question is, if we are given data from such a system and we know the causal structure, can we somehow estimate the causal effect from X to Y? And if so, how do we do it? The first question that we have to do is we have to say, well, what is the causal effect? And here the do notation comes in handy. So we are given the graph and the distribution of some data, and we want to compute the causal effect from X to Y. And how do we define it? This is one way of defining it. So what is written here? We are saying, well, we are intervening on X. So this means like you're forcing a certain person to have a certain diet. Of course, only hypothetical now. So we are saying you should have this diet, no matter what your sports habits are, no matter what other, like how old you are, you have to take this diet now. And then we are looking at the expectation of Y. So we're looking at the expected health outcome under this intervention. So this is how we write it, right? It's an expectation of y, but not under the observed distribution, but under an interventional distribution where we set x to little x. And now we are interested in how much does the health status increase if we sort of move towards this diet. And some of you also asked something about treatment effects and so on. This is really what it is here. So if you have a continuous treatment, so if x is continuous, let's say, I don't know, how many apples to eat or how much vitamin C or something, then it's roughly, maybe roughly continuous. Then you can look at now at the derivative with respect to x, right? We are looking at the expected value of the health outcome. If we intervene, if we force someone to take a certain treatment, and now we say, how much does this change if we change x to a certain amount? Now, if everything is linear, then this expected value of y is really, as a function of x, is a linear function, and then we can just see, well, what is the slope of this linear function. So if everything is linear, then this is a reasonable definition of a causal effect. Now, you may disagree with this. You may say, no, I don't like this. I want to have another definition of a causal effect, and that's totally fine. In a linear system, however, this is what a lot of people consider reasonable. So you're saying, looking at the expected value of y and an intervention on x, and now I see how much do I see an increase in the expected value of y. And now intuitively, hopefully what you see is in order to get this effect, now this red path doesn't matter anymore. And why? Because if I intervene on x, well, then this red path is sort of not there anymore. The question is now, can we somehow estimate this if we don't have access to the interventional data, but if we only have access to the observational data? And this is this problem is called, this is studied a lot, and this has, like, there are many different techniques, and maybe you have heard about covariant adjustment, maybe you have heard about doubly robust methods, maybe you have heard about targeted learning, maybe you have heard about propensity score matching. They are all sort of part of this goal of saying we want to estimate a causal effect like this if we are only given observational data and we know something about the causal structure. They all fall into this category. And here we are only talking about one of such methods, and then hopefully this enables you to read about the others as well. Okay, just to finish this line of thought regarding the treatment effect. So if you, for example, have a binary treatment, so you say either you get the treatment or not, then of course I cannot take the derivative with respect to x because x only takes two values. What would you do then? Then, for example, people look at the expected value of y under the intervention x being 1 minus the expected value of y under the intervention x being 0. So in some sense, this is very much similar to a sort of gradient, but now it's not a differentiable function anymore. So we take, if you like, the finite differences here, but it's the same spirit. How do you, by the way, define a causal effect if you have nonlinear systems? Still an open research question, I think. So if you have a good idea, then write a paper about it and let me know, because I think it would be nice to find some good. There are a couple of proposals, of course, but I don't think that there's something like in the linear case where most people agree. But maybe you have a good idea and then you write a paper. So then let me know. Would be interested. Okay, so this is the question, right? How can we compute this thing from the distribution and the graph? And I'll skip this maybe. So what we are going to talk about is adjusting. Now, what is adjusting? It's really, again, computing interventional distributions from observational distributions and the graph. And here's what you can do in linear Gaussian models. I'm now explaining it, and then we will have an exercise about this topic in a minute. So we say that Z is a valid adjustment set, and this is not defined here, but we will see it in a second. Then if Z is the valid adjustment set, then we can compute this value by regressing y on x and z and taking the coefficient in front of x. So let me go back to this example here. So in this example, if we want to estimate this effect, we cannot just regress y on x. Why is this? Because if you just regress y on x, then you get this sort of a mix-up between the dependence that is due to this causal path x goes to d goes to y, what we are interested in, but also this sort of bad path, this red one, that is due to the dependence of, let's say, whether you do sports or not. So regressing y on x doesn't work. But if you now regress y on x and, let's say, a, for example, then you can take the coefficient in front of the x, and this is a consistent estimator for the causal effect. So now people are doing this in practice a lot. So you see that if you're in applied sciences, you see studies where they're just throwing a lot of covariates and trying to adjust for a lot of confounding. But here, it's really if you look at the language, one has to be a bit more careful than that. You cannot just throw in any variable that you like. So, and you're trying this out in a minute, because some of them will just give you wrong answers. You can only throw in the variables that are called a valid adjustment set. And the next exercise is a bit about trying to find out how can we find valid adjustment sets. So what are the variables that I really have to put into the regression, and what are the variables that I must not put into this regression? But this is the definition. So Z is a valid adjustment set if, or more or less, so if this is a valid adjustment set, then I can obtain the causal effect by regressing y on x and z. So I'm adjusting for z and then take the coefficient in front of x. And here are some rules, and they are actually not very difficult to prove, but here I'm just going to state them because I thought it's maybe nicer to try them out rather than seeing the proof. So one set that always works are the parents of x. So the parents of x are always a valid adjustment set if you want to estimate the causal effect from x to y. Sort of an interesting insight. This always works. And now another, like a more general rule, and this is now if you know about d-separation. So otherwise, this is an intuitive rule now. So assume that you have a set z that blocks all vector paths from x to y. What is a vector path? A vector path is a path that starts with an incoming edge into x. Then z is a valid adjustment set for x and y. So what does this mean? This is now, for those of you who do not know about d-separation, don't worry. This is you just have to take this as an intuitive rule. For the others, it's a formal rule. I go back to this example. It somehow says that, well, the problem are really these so-called vector paths. So for example, this red one, this is the problem. This is the one that you want to block somehow. And whenever you find a set of nodes that blocks all these vector paths, then this is a valid adjustment set. So these are the ones that you can use for in your regression. Okay, and now one alternative, and this you can do if you are really given access to sort of the full structural causal model. So if someone doesn't only write down the graph, but very unrealistic in real life, writes down exactly the structural causal model, so with all the coefficients, then an alternative, what you can do is you just go through the directed paths between x and y and you multiply the coefficients and then you sum over the directed paths. So this means, like here in this example, if you know the coefficients of these edges, you can just multiply them between x and d to y, and then you get also the causal effect here. Okay. So now I'm looking at the clock. So we have about 15 minutes. So James, what do you think? We could start the exercise and then just come back at like 3 minutes before 11 and then discuss the answers tomorrow. Shall we do that? Or shall we just shift the exercise entirely to tomorrow?
Yeah, I think up to you. I'm good in either ways.
Okay, so then let's maybe look at some of the questions first, and then you can introduce the exercise, and then we see whether we have time to work on this. Otherwise, we do this first thing tomorrow.
Okay, sounds good.
First question: what is the major issue with nonlinear systems? So it's just if you look at this definition of looking at the expected value of y, if you intervene on x, this is a good thing. But now the question is, well, how much does it change? Now, if you have a nonlinear function, then usually the expected value of y under the intervention that you set x to x, this is not a linear function of x anymore, but it's just some nonlinear function of x. And now the question is, well, do we want to summarize this whole function by one number? So basically the question boils down to, well, what kind of little x do you want to use here? Also, you can maybe use this whole distribution on x, but then the question is, well, what kind of distribution do I choose on x? So then you run into these questions. In the linear case, it's somewhat simpler because then this relationship is just linear. Next question. In real life, many variables events interact to suggest causality. How do we detect the difference from another variable? This I'm not 100% sure I understand. Maybe you can try to clarify the question in the chat. So next question. So when you want to find valid adjustment set in the real world, how do you go about it? What if you're unsure about the graphical model in the first place? So I like that question a lot, and it's indeed a problem that sometimes people have an idea of some of the confounding paths. So maybe you have an idea that there's one path that, and then you can be certain that this I somehow have to block. But now the question is, well, can there be other paths as well? And even worse, can there be some paths that I don't even observe? And this we are going to talk about first thing tomorrow, I think. Let's say you're unsure if there's a connection from A to Y at all, but you still want to consider A as a possible covariate. So here, if I may, I would rephrase this comment, because it's somewhat whether or not you want to use something as a covariate is really boiling down to the fact whether you're looking at a valid adjustment set or not. So I know that in really many practical applications, people are coming up with all sorts of covariates and just putting them into the regression model and then looking at the effect of X. And I do not think that's a good idea. I think it's a better idea to first sit down and say, okay, what could be my causal model? You write down a graph like this. And now you're saying, what do I have to put into the covariate in order to get an unbiased estimate from X to Y? And this is really the notion of a valid adjustment set. And I gave you two rules of deciding whether something is a valid adjustment set, but you're more than welcome to look into the book. For example, there's a characterization, a more formal characterization of what a valid adjustment set is. Now, this is really the correct mindset in my point of view. So you think about what do I know about the causal structure, and then what do I have to put into the regression? Because as you're going to see, if you can put too many variables into the regression. So it could be that if you're putting too many variables in here, you actually get an unbiased estimate. Okay, and then regarding this concrete thing, if you're uncertain about there's a connection from A to Y, but then, so if for example, you look at this rule here, right? The parents of X is a valid adjustment set. Then if you look at this graph, it actually doesn't matter whether this part of this red path here, whether this exists or not. So the parents of X are always a valid adjustment set. So I can always use C and A no matter what is happening here on the right hand side. This is a bit of a nice scenario here. Okay, you know what, James? What I propose to do is I talk for 4 more minutes, and then you introduce the exercise, and then we are going to start on this next thing tomorrow morning. Okay, so next question is, could you comment about dynamic causal modeling that is used in fMRI studies? So this is really a broader topic. This would be a bit of a longer discussion. We have actually a section on this in the book as well, in case you are interested. There's a lot of debate also around this, but what is maybe if you want to navigate these debates, what I usually think is helpful to say is, well, write down, okay, what we are going to see, this is regarding causal structure learning. So can we learn causal structure from data? And we are going to see one example tomorrow. And I think there, the following idea is actually helpful. So causal structure learning is impossible without assumptions, in the sense that there are different structural causal models inducing the same observational distribution. So we cannot, if we are just given the observational distribution, find the structure, unless we are willing to make more assumptions. And I think it's always very helpful to be very explicit about the assumptions. So we are going to see one type of assumption tomorrow under which this becomes possible. There are many others as well. This is an active field of research where people are trying to find a different set of assumptions under which this becomes possible. And I think it's always important to navigate literature with this way of thinking. So what is the underlying assumption that makes me able to identify causal structure from data? But there's really a question that that concerns the topic of tomorrow. Okay, so one last question I'm going to talk about today, and then I hand over to James. In the first table comparing different types of models, the physical insights from causal models was marked with a question mark. Is the lack of clarity about physical insight from causal models coming from a lack of real experiments to check these causal models? So this is this table that I had at the beginning here. So let's look at this problem that we are considering right now. So right now, if we have a causal model and some observational data, you will be able in this exercise to compute or to estimate a causal effect from X to Y. So you will be able to consistently, using these valid adjustment sets, estimate, well, what happens to Y if I intervene on X. And I would say this is some physical insight. So this is some insight on saying how the different parts of your system interact with each other. However, it's not full physical insight in the sense that you cannot write down like a model from first order principles. So think really about maybe this example from in the medical domain where we don't know how a certain drug works in the brain, what it does, but we have a good understanding of how much we have to give to a certain person. Do you call this physical insight or not? Some people may say yes, some people may say no. This is why I put the question mark there. Okay, but now really back to this valid adjustment set. So this was a bit of a detour. So again, what's the problem? We're given a graph, we are given some data, and now we are trying to estimate this effect. And maybe James can just introduce the exercise now, and then we'll start doing it tomorrow.
Yes, sure. But quickly, I think you may have missed one. I think someone asked about the reference for the causal effect for nonlinear models.
Yes, yeah. So I think what's the easiest thing is to just Google. There are a couple of references, but as I said, there's not there's not such a consensus as in the linear world.
Okay.
So I propose to just Google for nonlinear models, causal effect, and then you'll find the references that are relevant.
All right, let me then share my screen now. Quickly, we have a few minutes. Sorry. All right. So in the same notebook, we will see exercise 2 adjusting. And this is the same SCMs with the same graph. And we have a couple of questions about the adjustment or estimating the causal effect by finding the valid adjustment set. I think more importantly, you can, I think A, you can already answer, and B, Jonas already mentioned about the 2 recipes that we can use. But I think the main thing, sorry. Sorry, I think something is wrong with my room. Maybe we can move it to tomorrow. Sorry.
I can maybe just finish. Sorry for that. So the second question, right, is the different recipes for constructing valid adjustment sets. Then the third one is really trying it out, and this I highly recommend doing this. And I know that a lot of people from you join the record rooms, some others do not. In any case, really try this out. I think it's very important to see this once in practice. And then the D, if I remember correctly, this is just if there's another one, this is just the question of like, why could it be interesting to have several options for choosing a valid adjustment set? So this is a bit weird, right? So if I have one recipe, why is this not always enough? Could be I can just always use this one. So why could it be interesting to have more? And then if you indeed have access to several valid adjustment sets, what would you do? Okay, so these are the questions. We are going to talk about this tomorrow morning, and then we are going to have like more time for the questions that I wrote down. And if in case you have something else that comes to your mind, just let us know tomorrow morning, and then we can hopefully adjust. Good. Thanks for today. That's all what we wanted to say. And then I hope that all of you have a nice afternoon or evening, or for the Europeans, a very nice day.